All right, today we are going on a grand tour deep inside one of the body's most amazing organs, the kidney. We're going to peel it back layer by layer, from where it sits in your body all the way down to the tiny microscopic engines that do all the work. So let's get started.
So, the urinary system, it's really a beautiful piece of engineering. You've got your two kidneys, two ureters, which are like the plumbing pipes, one bladder for storage, and one urethra to get rid of the waste. But just getting rid of waste, that's barely scratching the surface. This system is a master of what we call homeostasis, which is basically your body's way of keeping everything in perfect balance, constantly fine-tuning your blood's pH, its volume, and even your blood pressure.
Okay, here's a little pop quiz to get us going. What organs are so small they make up less than 0.5% of your body weight, but, and get this, they demand a whopping 25% of all the blood your heart pumps out? The answer? Yep, you guessed it, the kidneys. And that massive blood flow tells you everything you need to know about how vital their job really is. So, first things first, where exactly are these little powerhouses hiding? You might actually be surprised. They're not just floating around in your belly with your stomach and your intestines. No, their location is way more protected. Here we can see their exact address. The kidneys are snuggled way up high against the back wall of your body, right between the T12 and L3 vertebrae. And you might notice, the right kidney sits just a little bit lower than the left one. And why is that? Well, it's got a big upstairs neighbor. The liver is literally pushing it down. And this brings us to a really important term, retroperitoneal. I know, it sounds super technical, but it just means behind the peritoneum. See, the peritoneum is this slick, slippery lining inside your abdomen, and unlike most of your digestive organs, the kidneys are tucked safely behind it, which gives them fantastic stability and protection. Okay, so not only are they in a safe neighborhood, but the kidneys also come with their own personal suit of armor. Let's take a look at the 3 different layers that wrap around each one. So, working our way from the inside out, first you've got the fibrous capsule, which is this tough layer that holds the kidney's shape. Then, wrapped around that is a nice thick cushion of fat called the perirenal fat capsule, which acts like a shock absorber. And finally, the outer renal fascia anchors the whole thing securely to your body wall. And you can really see here how these layers just team up. The capsule provides the shape, the fat gives it cushioning, and the fascia locks it all down. It's a complete 3-part defense system. Now that we've seen the outside, let's venture deeper. If we were to slice a kidney right down the middle, we would immediately see 2 very, very different regions inside. And wow, the contrast is pretty dramatic. The outer part, the renal cortex, is a lighter red color and has a smooth texture. But then you look at the inner renal medulla, it's much darker, a deep reddish brown, and it's packed with these cone-shaped structures called renal pyramids. And these are the guys that do the heavy lifting of making urine.
Looking at this diagram here, you can clearly see those cone-shaped things in the medulla. Those are the renal pyramids. The pointy tip of each pyramid, we call that the renal papilla, points inward. And the stuff separating the pyramids, those are the renal columns, which are really just extensions of the outer cortex diving down. This whole structure creates this perfect drainage system, kind of like a funnel. Fluid drips from the tips of the pyramids, the papillae, and it gets collected by these little cups called minor calyces. A few of those merge to form a bigger cup, a major calyx, and then all of those pour into one big basin, the renal pelvis, before everything flows out of the kidney down the ureter. All right, buckle up, because this is where our journey gets really detailed. We are now zooming way, way past what the naked eye can see, deep into the microscopic world of the nephron. This is the real workhorse of the kidney. So get ready for a number that's kind of hard to wrap your head around. Every single one of your kidneys is packed with about 1 million of these little filtration factories. That's right, 1 million per kidney. It's just an incredible density of processing power. So what exactly is this microscopic engine doing? Well, the nephron has one main job, filter your blood and make urine. And you can think of it as having 2 main parts, the renal corpuscle, which is the filter itself, and then this long, winding renal tubule, which is where all the filtered stuff gets processed. And here's where it gets even more interesting. It turns out, not all nephrons are created equal. As you can see here, the vast majority, we're talking 80 to 85%, are what we call cortical nephrons, and they have these short little loops. But then there's this other crucial group, the juxtamedullary nephrons. And that difference in their loops, that's their superpower. Cortical nephrons have short loops that barely even poke into the medulla, but the juxtamedullary nephrons, they have these incredibly long loops that plunge way down deep into the medulla. And it's these long loops that give the kidney its amazing ability to make highly concentrated urine. It's a game changer. Okay, last, but definitely not least, let's talk about the fuel for this whole operation. Because none of this amazing filtration could ever happen without an absolutely massive blood supply. So let's trace the path of this vascular superhighway. Just to hammer this home one more time with this staggering fact, at any given moment, your kidneys are getting 20 to 25% of all the blood your heart is pumping. Why so much? Because they have to process your entire blood volume over and over again, filtering about 180 liters of fluid every single day. Just incredible. So blood comes rushing in through this huge renal artery, and then it travels through a series of smaller and smaller branches. Think of it like a big tree branching out, until it finally reaches the afferent arteriole. This is the last tiny little vessel that delivers blood right to the filter. And this is a truly bizarre setup. You won't find it anywhere else in the body. The glomerulus, that's the little ball of capillaries where filtration happens, is sandwiched between two arterioles. Everywhere else, blood flows from an arteriole to a capillary to a venule. But this special design lets the kidney crank up the pressure inside the glomerulus, which is exactly what you need to force all that fluid and waste out of the blood.
This slide here shows you the whole circuit. So after that high pressure filtration, the blood flows out into a second set of capillaries. These are either the peritubular capillaries, which wrap around the cortical nephrons, or the super specialized vasa recta that follow those long loops of the juxtamedullary nephrons. This is where all the good stuff gets reabsorbed before the clean blood finally heads back out through the renal vein. And there you have it. A complete journey through the kidney's anatomy, from its cozy spot in your back all the way down to its microscopic blood supply. We've mapped out the entire structure, the whole blueprint. But that just leads to the next big question. How does the actual filtering happen? What's the magic behind it? Well, for that, you'll have to join us for our next explainer.
You know, deep inside your body, there's a filtration engine that's so powerful it processes your entire blood supply more than 60 times a day. It's pretty amazing. Today, we're going to dive into the incredible physics and biology of the kidney that make this whole thing possible.
So let's just start with a number that is kind of hard to wrap your head around. 180 liters. That's how much fluid your kidneys filter out of your blood every single day. Seriously, try to picture an entire bathtub filled to the brim. That is the sheer scale of what we're talking about.
So this obviously leads to a massive question. How on earth does your body manage a task this big? I mean, how does it filter all of your blood, dozens and dozens of times a day with such incredible precision, and all completely on autopilot?
Well, it turns out the kidney has this surprisingly elegant, almost simple master strategy. It's a highly coordinated three-step mission that keeps our blood perfectly, and I mean perfectly, balanced.
The whole strategy really boils down to just these three pillars: filtration, reabsorption, and secretion. You can think of it as a filter everything first, asks questions later approach. It's a totally brilliant system for making absolutely sure that nothing bad gets missed.
Okay, let's break that down. Step 1 is glomerular filtration, and this is kind of the brute force stage. The kidney just dumps a massive amount of water and all the small stuff, the good, the bad, all of it, out of the blood. It's completely non-selective.
But of course, the body is no fool. So, in step 2, tubular reabsorption, it meticulously goes back and reclaims about 99% of all the useful things that just pushed out. We're talking water, glucose, essential ions, all the good stuff.
And then finally, we have step 3, tubular secretion. Think of this as the absolute last call for trash. The kidney actively kicks out any leftover waste, maybe some drugs, and any excess ions into what's going to eventually become urine.
For the rest of our time together today, we're going to zoom right in on that first and maybe most dramatic step, the incredible filtration machine itself. So this entire process, this massive filtration job, it all happens inside a microscopic structure that basically works like a super sophisticated 3-layered sieve. Let's take a look at how this thing is actually built. Okay, so the 3 layers we're talking about are the endothelium, the basement membrane, and these cool cells called podocytes. That first layer, the endothelium, is what we call fenestrated, which is just a fancy way of saying it's full of tiny little pores. And each of these layers has a very, very specific job in this high-tech filter.
And here's how they all work together. The first layer, that porous endothelium, it acts kind of like a colander, stopping the big stuff like blood cells. Then the middle layer, the basement membrane, uses a negative electrical charge to literally repel big proteins. And then the final layer, the podocytes, they wrap around the whole thing and form these tiny little filtration slits, creating a final barrier that only the absolute smallest molecules can get through.
You know, a really great way to think about that first layer is to just picture a pasta strainer. It lets all the water and small stuff, the pasta water, pour right on through, but it's tight enough to hold back the big things, like your red blood cells and platelets.
Okay, so we've built our high-tech filter, but what's actually pushing 180 liters of fluid through it every single day? Well, the answer comes down to pure physics and a constant, really delicate tug-of-war between opposing pressures.
The key concept here is something called net filtration pressure, or NFP. The easiest way to think about it is as the final score in that tug-of-war. It's the battle between the main force that's pushing fluid out of the blood and 2 other forces that are trying to push it right back in.
This diagram shows that battle perfectly. On one side, pushing fluid out of the blood, you have the main force. That's the blood pressure inside the filter, which is about 55 millimeters of mercury. But fighting back, you've got 2 forces pushing fluid back in. There's some back pressure from the fluid that's already in the capsule. And then there's something called osmotic pressure, which is just the natural pull of water back towards the proteins that are still in the blood.
So when you do the math, it's actually a really simple calculation. You've got that powerful 55 millimeter of mercury force pushing out and a combined 45 millimeters of mercury of force pushing back in. So 55 minus 45 gives us our final net pressure.
And the result is just 10 millimeters of mercury. Just 10. I mean, think about that for a second. This entire massive filtration process, all 180 liters of it, is driven by this tiny, really delicate net pressure. It's a system of incredibly powerful forces held in this unbelievably precise balance.
Now, maintaining that delicate 10 millimeters of mercury balance is absolutely critical. So you have to wonder, How does the kidney stop the whole system from going haywire whenever your blood pressure changes? Well, it uses its own brilliant autopilot system called renal autoregulation. See, the one thing we need to keep constant is the glomerular filtration rate, or GFR. And we want this in a Goldilocks zone. Not too high, not too low. Right around 105 to 125 milliliters per minute. If it's too high, we start losing good stuff we need. If it's too low, we don't clear out waste effectively.
And the kidney's autopilot has two main tools in its toolbox to protect that GFR. First up is the myogenic mechanism, which is a super fast physical reflex. And the second is something called tubuloglomerular feedback, a slower but way more high-tech chemical feedback loop.
Let's start with the myogenic mechanism. It's so simple, it's honestly genius. As you can see here, when a spike in your body's blood pressure physically stretches the artery that leads into the filter, the muscle in that artery wall just automatically contracts in response. It narrows the pipe, which reduces blood flow and protects the delicate filter from that big pressure spike. Now, the second system, tubuloglomerular feedback, is a bit more high-tech. If the filtration rate gets too high, fluid starts rushing through the tubules too quickly for nutrients to get reabsorbed. So special sensor cells, called the macula densa, they detect the high salt content in this fast-moving fluid. In response, they send out a chemical signal that basically tells the artery to constrict, slowing blood flow down and bringing the filtration rate right back to normal.
So, to put it all together, your kidneys are filtering an absolutely incredible 180 liters of fluid every single day. They're doing it through a microscopic 3-layer sieve. This whole powerful process is driven by a tiny, delicate pressure of just 10 millimeters of mercury, which the kidney masterfully protects with its own intelligent autopilot system.
The system is powerful, for sure, but it is also incredibly delicate. So, with this entire filtration engine held in a perfect, fragile 10 millimeter of mercury balance, what happens when it breaks? What happens when that balance is finally lost?
Today, we are diving into one of the most incredible, most vital engineering feats in the entire human body, the kidney's ultimate reclamation mission. Seriously, this is a process so essential that if it stopped, our bodies would shut down in a matter of minutes. Let's get into how it all works. All right, let's just start with a number that's kind of hard to wrap your head around. 180 liters. That's about 45 gallons. We're talking a full-sized bathtub's worth of fluid. And that is the amount of fluid your kidneys filter out of your blood every single day. So you can see the problem, right? If your body just let all of that go, you'd lose your entire plasma volume in, like, minutes. This reclamation process isn't just a nice to have. It is a constant, nonstop, life or death rescue operation. So how in the world does the body pull it off? Well, the answer, the hero of our story really, is a process called tubular reabsorption. It's the official term for that massive rescue mission. It's where the cells lining the kidney's tubules grab about 99% of the water and all the useful stuff, salts, nutrients, and puts it right back into the blood where it belongs. So let's put on our hard hats and take a tour of this incredible reclamation factory. Our first stop, it's the main assembly line, the part that does pretty much all the heavy lifting, the proximal convoluted tubule, or as we call it, the PCT. So here you can see on this map of the nephron, the PCT is that very first squiggly part of the tubule right after the main filter. You can think of it as an absolute powerhouse. It's built with this dense brush border to maximize its surface area for one primary job, grabbing almost everything back. And the workload here is just immense. The PCT reabsorbs about 2/3 of all the water, sodium, and potassium right off the bat. But maybe its most critical job is reclaiming 100%, not 99%, 100% of vital things like glucose and amino acids. Your body literally cannot afford to lose a single one of those molecules, and the PCT makes sure it doesn't. So that just begs the question, right? How on earth does it manage that? How does the PCT achieve this perfect 100% score on reclaiming something as precious as glucose? Well, the mechanism it uses is just incredibly clever. It uses this amazing trick. So first, the cell burns a ton of energy to pump sodium out. This creates this powerful vacuum, making sodium desperate to rush back in. Then, you have this special protein on the cell's surface that acts like a bouncer at a club. And this bouncer has a strict +1 rule. It will only let a sodium ion back in if it brings a glucose molecule along with it. The glucose basically gets a free ride, powered entirely by sodium's mad dash to get back inside the cell. Okay, so once the PCT has done all that heavy lifting, the fluid moves on to the next section, the loop of Henle. Now, this part of the factory isn't about just grabbing stuff in bulk. Oh no, it has a much more specialized and, frankly, brilliant job. It's the concentrator. And this is where the plot really thickens, because the two sides of this loop do the exact opposite things. The descending limb, as it dives deep into the kidney, it's basically a net made only for water. Water can leave, but salts are trapped inside. So as it goes deeper into the salty part of the kidney, water just rushes out and the fluid inside gets super concentrated. But then, on the way back up, the ascending limb flips the script. It's completely waterproof, but its walls are packed with powerful pumps that are actively throwing salt out into the surrounding tissue. This makes the tissue incredibly salty, and the fluid left inside becomes really dilute. This whole genius system, with fluid flowing in opposite directions and each side playing by different rules, has a name: countercurrent multiplication. It's an unbelievably efficient design that uses this opposing flow to build and maintain a massive salt gradient. And that gradient is the secret weapon that allows our body to finely tune our water balance later on.
This brings us to the final stretch of reabsorption, the distal convoluted tubule and the collecting duct. You can think of this as the quality control department of the factory. This is where the body makes tiny, precise, hormonally controlled adjustments to meet its exact moment-to-moment needs. And this fine-tuning is handled by two types of specialist cells. First, you've got the principal cells. They're in charge of salts and water balance, and they basically take orders from hormones like ADH and aldosterone. Right next to them, you have the intercalated cells. Think of them as the body's pH managers, meticulously handling our acid-base balance by either reclaiming bicarbonate or kicking out hydrogen ions. So up until now, we've focused on saving all the good stuff, but the factory's job isn't quite done. It also has to actively take out the trash, the stuff that the initial filter might have missed. And this is where a second, equally important process comes into play: tubular secretion. And that might make you wonder, right? If the kidney's filtration is so powerful, why would it even need a separate system for getting rid of waste? Why not just filter everything out in the first place? Well, the simple answer is that the filter isn't perfect. A lot of things, including really common drugs like penicillin and other metabolic wastes, they kind of hitch a ride through our blood by latching onto really big proteins. They're just way too big to get squeezed through that initial filter, so filtration alone can't touch them. So tubular secretion is the solution. It's an active transport system that literally pulls these substances out of the blood in nearby capillaries and pumps them directly into the tubular fluid. It's the kidney's way of making absolutely sure that what can't be filtered out still gets thrown in the trash. And this is where it gets really fascinating from a medical standpoint. We can actually manipulate this process. Because a lot of drugs are weak acids or bases, doctors can change the urine's pH to trap a drug in the filtrate. This prevents the drug from being reabsorbed back into the body and forces it to be excreted much, much faster. An absolutely crucial tool for treating things like a drug overdose. So when you look at the whole picture, it's really a perfect partnership. Reabsorption saves all the essential stuff. Secretion gets rid of all the unwanted leftovers. It's beautiful, really. They are two sides of the very same coin, both working around the clock to keep your body in perfect balance. And this is the incredible final result of all that work. You take that massive 180 liters of initial filtrate, and through this masterful process of reabsorption and secretion, it gets refined all the way down to just about 1.5 liters of final urine, a final product that's perfectly tailored to exactly what your body needs in that moment. This elegant, incredibly complex factory works tirelessly, 24/7, to maintain the delicate balance of your entire internal world. But it also raises a pretty critical question. What happens when this perfectly tuned machinery begins to break down? Well, that's a story for another time.
All right, let's talk kidneys. But for a minute, I want you to forget everything you think you know. Today, we're pulling back the curtain on the kidney's secret identity, because it's not just a filter, it's a powerful command center running some major operations in your body. And look, if your first thought was, it's a filter, you're not wrong. That's what we all learned, right? It's this amazing biological cleaning system for our blood. And yeah, that job is absolutely vital. But what if that's just scratching the surface? What if that filter job is like the kidney's day job and it has this whole other secret life? A much more powerful, commanding role that we're about to dive into. So this is the perfect way to look at it. On one side, you've got the job we all know, the passive filter. But on the other side, you see its real identity, an active, powerful command center, an endocrine gland that's calling the shots and sending out crucial chemical orders.
So let's jump into the first of these major commands. Command number 1 is make blood. And no, you did not hear me wrong. The whole process of making new red blood cells, it doesn't start in your bones, it starts right here, in the kidneys.
You see, the kidney is basically the body's ultimate oxygen sensor. Think about it. Every drop of your blood is constantly flowing through it. And all along the way, specialized cells are just sampling, constantly checking oxygen levels. The second they sense a dip, a condition we call hypoxia, they sound the alarm. And that alarm is a hormone called erythropoietin, or as you've probably heard it called, EPO.
You can picture EPO as this urgent memo shot out from Kidney HQ, sent directly to the red blood cell factories located in your bone marrow. And the message is crystal clear. Hey, we're running low on oxygen carriers down here. You need to ramp up production like yesterday.
And this is what's so incredible. The kidney isn't just part of the team here, it's the superstar. A whopping 89 to 95% of all the EPO in your body is made right there. Yeah, the liver chips in a tiny bit, but the kidney is, without a single doubt, running the entire show.
And this is where it all connects to the real world. This is why it matters so much. When someone has chronic kidney disease, their kidneys start to fail. And when that happens, that primary signal, that order to make red blood cells, it just gets cut off. The bone marrow is just sitting there, waiting for instructions that never arrive. And that is why severe anemia is almost always a devastating part of chronic kidney disease.
Okay, so the kidney is in charge of blood production. Pretty amazing, right? Well, it's just getting started. Its next big command is to build strong bones. And the way it does this is all about vitamin D.
Now here's the key word you've got to remember: active. You see, the kidney creates something called calcitriol, and that is the only active form of vitamin D your body can actually use. Without it, you could eat all the calcium in the world, and your intestines just can't absorb it. Calcitriol is literally the key that unlocks the door for calcium to get into your body. I love this analogy. Think of it like a relay race. The race starts when you get inactive vitamin D, either from sunlight or from food. The liver takes the baton for the first leg and does a quick conversion. But the kidney is the anchor. It runs that final, all-important leg of the race, performing the last critical chemical step to create that useful active calcitriol.
And make no mistake, without the kidney finishing that race, the whole thing falls apart. The process just stops dead in its tracks, and your body is left completely unable to get the calcium it desperately needs for your bones. All right, we've had blood, we've had bones, now let's get to the kidney's third and honestly probably its most powerful command of all. If the kidney is the command center, then this next system, the renin-angiotensin-aldosterone system, or just RAS, well, this is the master control panel for your body's entire blood pressure.
Now, what is RAS? Well, it's this incredibly smart, complex chemical chain reaction. It's a system designed for one main purpose, to keep you alive if your blood pressure or your fluid levels ever suddenly plummet. So let's break it down step by step. It all starts when the kidney senses your blood pressure is dropping. Bam! It releases an enzyme called renin. Renin then finds a protein that comes from the liver and converts it into something called angiotensin 1. But angiotensin 1 is just a stepping stone. As that blood flows through your lungs, an enzyme called ACE jumps in and converts it into the real heavyweight champion of this system, angiotensin 2. And then finally, angiotensin 2 tells your adrenal glands to release one more player, a hormone called aldosterone.
And let me tell you, angiotensin 2 is an absolute powerhouse. It is one of the most powerful blood vessel constrictors your body has. Its effect is almost instant. It squeezes arteries everywhere, all at once, to just crank your blood pressure right back up. It's like flipping the emergency override switch for your entire circulatory system.
But angiotensin 2 is a smart multitasker. While it's handling the immediate crisis, it's also playing the long game. It signals the adrenal glands to release aldosterone. Aldosterone is the long-term solution. Its job is to go right back to the kidneys and tell them, hey, hold on to more sodium. And we all know the rule, where salt goes, water follows. This increases the total amount of fluid in your pipes, which is a much more stable long-term fix for low blood pressure.
I mean, it's a beautiful system, isn't it? It's brilliantly designed to save your life. But, and this is a huge but, here comes the tragic twist. When you're dealing with chronic high blood pressure, this amazing, life-saving system, it turns on itself. It becomes the very thing that fuels its own destruction.
This analogy just paints the perfect picture. Imagine taking a high-pressure fire hose and aiming it at a delicate silk screen. That is exactly what chronic high blood pressure is doing day in and day out to the tiny, delicate filters inside your kidneys. It's just this relentless, damaging blast.
And over time, that constant pounding causes real physical damage. It leads to scarring and thickening of those fragile little filters. The medical term for it is nephrosclerosis. And it's this physical damage that kicks off one of the most vicious cycles in all of medicine. So here's how it works. Step 1. The damage from the high pressure actually reduces the blood flow inside the kidney. Now, the kidney is brilliant, but it has a critical design flaw, a huge blind spot. It can't tell the difference between low blood flow right here, locally, and low blood pressure throughout the entire body. So it freaks out. It thinks the whole system is crashing. So what does it do? It smashes the big red button for the RAS system to fix the problem, which of course just skyrockets the blood pressure even higher.
And there it is, the feedback loop from hell. High blood pressure damages the kidney, and then the damaged kidney, trying to help, makes the blood pressure even higher, which causes even more damage. The kidney's own survival mechanism becomes the engine of its own destruction. So let's bring it all home. We started out thinking of the kidney as just a simple filter, right? But now we know the truth. It is so much more. It's a systemic commander-in-chief, issuing powerful, non-negotiable orders that control our blood, our bones, and our blood pressure.
Which leaves us with one last thought. Now that you know the kidney isn't just a passive victim of high blood pressure, but it's actually an active participant in that destructive cycle, how does that change how you think about the importance, the absolute urgency of keeping your blood pressure under control?
All right, let's talk about one of the most incredible organs in your body. And it's probably not the one you're thinking of. I'm talking about the kidney. And you know, we often think of it as just a filter, right? But that's not even half the story. The kidney is really the master regulator of our entire internal world. It's so much more than a simple filter. So let's get into it. Okay, I'm just going to throw a number at you. 180 liters. That's, what, nearly 50 gallons? So what on earth could that massive volume represent?
Well, believe it or not, that is the absolutely staggering amount of fluid that your kidneys filter from your blood every single day. But here's the kicker. Making urine isn't even their main job. Nope, that's just a byproduct of their real mission, their most important mission, maintaining the delicate balance, what we call homeostasis, that literally keeps you alive. So yeah, it's pretty clear we need to think way beyond the whole simple filter idea. The kidney's true purpose is so much more intricate and absolutely essential.
It really all boils down to one crucial concept, homeostasis. You've probably heard the word, but what is it, really? Well, it's all those tiny, constant adjustments your body makes to keep your internal world stable and just right, no matter what you're eating or drinking or how much you're exercising. And when it comes to that job, the kidney is the undisputed champ, the master regulator of the whole show.
All right, let's look at one of the kidney's most amazing feats. It's like a high-wire balancing act, and it's all about managing the pH of your blood. And when I say this is critical, I mean it's literally a matter of life and death.
So check this out.
Your blood has to stay within this incredibly narrow pH range. We're talking 7.35 to 7.45. If it dips a little too low or goes a little too high, your cells just can't function. They start to shut down. So how in the world do the kidneys pull this off day in and day out?
This is where things get really cool. The system is just so elegant. You've got these specialized cells in the kidney's tubules. They're called intercalated cells, and you can think of them like tiny little accountants for your blood's pH. Their job is to constantly look for excess acid, which comes in the form of hydrogen ions, and actively kick it out of the blood. But here's the genius part. For every single acid ion they boot out, they grab and reabsorb one bicarbonate ion, which is the blood's most important buffer. It's a perfect one-for-one exchange that keeps everything in balance. It's just wow.
And this table, this just puts the sheer scale of that operation into perspective. Just look at the bicarbonate ions. Your kidneys filter about 275 grams of this stuff a day. But how much do they reclaim? 274.97 grams. We're talking more than 99.9% is pulled back into the blood to keep that pH perfect. This isn't just filtering and dumping. This is an aggressive, incredibly efficient reclamation project.
So what's the takeaway here? Why does this matter so much? Well, this isn't just some neat chemistry trivia. When this whole accounting system fails, like in kidney failure, those hydrogen ions have nowhere to go. They build up and the blood becomes dangerously acidic. That condition, called metabolic acidosis, is a life-threatening emergency. Okay, so we've seen how this amazing system works, but it's important to remember that it isn't static. It changes throughout our lives. So let's rewind to the very beginning of the lifespan and talk about the developing urinary system in kids and some of the unique challenges they face.
Now, one of the most important things to know about in pediatric kidney health is something called a Wilms tumor. It's actually the most common type of kidney cancer you see in children, and it usually shows up when they're really young, like 3 or 4. It basically comes from kidney cells that just didn't mature the way they were supposed to. But, and this is the really key point, the good news is that treatment is incredibly effective. With surgery and chemo, it's highly curable.
This really paints a picture of the two ends of the spectrum, doesn't it? On one hand, you have an infant's kidneys. They're still learning the ropes. Their parts are immature, so they're not great at concentrating urine, and they can't cope with dehydration as well. Then you fast forward a whole lifetime. Now you're looking at an elderly kidney. It's not about being immature anymore. It's about the decades of wear and tear, all that relentless work, which naturally leads to a decline.
So let's dig into that a little more. What exactly happens at the other end of the spectrum? How does a lifetime of nonstop work actually change the system?
Okay, so the best way to measure kidney function is something called the glomerular filtration rate, or GFR for short. Think of it as your kidney's horsepower rating. And as you can see here, aging is, well, it's a story of a slow but steady decline in that horsepower. It usually starts around age 40. From there, the GFR just keeps ticking downward. By the time someone is 70, their kidney's filtering power could be down by as much as 50%, half of what it used to be. And that's not just a number on a chart. It has real-world consequences. A lower GFR means it takes longer for the kidneys to clear things out of your blood. So what does that mean? It means older adults are way more vulnerable to certain medications. We call them nephrotoxic, or toxic to the kidney. The drug just hangs around in their system for longer, giving it more time to do damage. And it's not just the filtration rate. The changes happen across the whole system. The kidneys themselves actually get smaller. They can shrink by 1/3 by age 80. A huge percentage of the tiny filtering units, the glomeruli, just stop working. The bladder holds less, and to top it all off, that sensation of being thirsty can actually diminish, which is a huge problem. It creates this perfect storm for dehydration, which puts even more strain on the kidneys. So, we've seen the kidney as this incredible regulator, but what happens when it all fails, when it can no longer do its job? You get a full-blown systemic crisis called uremia. That's when all the waste products that are supposed to be removed build up and literally start to poison the entire body from the inside out.
It's a cascade of failures. First, the most basic jobs break down. The kidneys can't regulate salt and water anymore, so fluid just builds up everywhere. That's the swelling, or edema. Then there's potassium. It's supposed to be excreted, but now it's trapped. It builds up to toxic levels. That's hyperkalemia, and it can cause deadly heart rhythm problems.
And of course, just like we talked about, the acid-base balance is gone. The blood turns acidic. Metabolic acidosis sets in.
And it doesn't stop there. All those waste products are now circulating and poisoning every system. Those uremic toxins get into the brain, and you get what's called uremic encephalopathy. You're looking at confusion, cognitive decline. It's really serious. The toxins also damage nerves all over the body, and the gut takes a hit too, causing things like nausea, vomiting, and just a total loss of appetite.
And then there's the final piece of the puzzle, a job people often forget the kidneys even have, making hormones. When they fail, they stop producing a crucial hormone called EPO. Without EPO, your body can't make red blood cells, which leads to severe anemia. They also stop activating vitamin D. And without active vitamin D, you can't absorb calcium from your food, so your bones just get weaker and weaker, leading to severe bone disease. It really is a complete, total system meltdown.
So that brings us to the big takeaway. We've seen that the kidney isn't just a filter. It's this incredibly smart, complex regulator of our entire internal world. So knowing all this, how does that change the way we think about protecting our own kidneys? How much more urgent does it feel to really manage things like high blood pressure and diabetes, the two conditions that pose the single greatest threat to these incredible organs?
All right, welcome. Today, we are taking a trip through one of the most essential but maybe overlooked parts of your body, the lower urinary tract. We're going to see some amazing muscular engineering, really clever biological design, and the super precise nerve signals that make it all work. So let's just dive right in. So before we get into the nitty-gritty, let's just get our bearings with the big picture here. We've got the kidneys up top, and they are the absolute powerhouses of this whole operation, making the urine. But our focus, our journey today, is all about what happens after that, the final passage through the lower urinary tract. So what's on the itinerary? First, we're going to travel down these amazing one-way streets called the ureters. Then we'll land at the bladder, which is way more than a simple bag. It's a smart reservoir. From there, we'll unpack the command to go, a process called micturition. And finally, we'll look at what happens when this elegant system gets compromised. Okay, let's get started. Our first stop, the ureters. Now, you might think of these as just simple tubes, but they are so much more. They are active, muscular highways that really kickstart urine's journey out of the body. So what are we looking at exactly? Well, you've got two of them, one connected to each kidney. They're about 10 to 12 inches long, and they're tucked away really neatly behind the main lining of your abdomen, a position we call retroperitoneal. And their one and only job is to be the bridge from the kidneys to our next stop, the bladder. Now, this is where it gets really interesting. Let's peel back the layers of the ureter wall. On the inside, you've got the mucosa. It's super stretchy and coated in mucus to protect itself from the urine. Then you have the muscularis in the middle. This is the engine, the smooth muscle that does the pushing. And on the outside, the adventitia is like this tough anchor holding everything securely in place. And that middle muscularis layer is absolutely key. The big takeaway here is that urine doesn't just passively trickle down because of gravity. No way. It is actively pushed by these little waves of muscle contractions. That's called peristalsis. It happens about 1 to 5 times every minute, ensuring a steady, one-way flow, whether you're standing up, lying down, or even upside down. So this brings up a really good question. If you've got this active pushing going on, what stops the urine from just flowing right back up into the kidneys, especially when the bladder starts to get full? I mean, there's no mechanical valve here like you'd find in your heart, so how does the body pull this off? And the answer is just, well, it's brilliant. It's a physiological valve. See how the ureters enter the bladder wall at an angle? As the bladder fills up and the pressure inside increases, it naturally squashes and pinches those openings shut. It's such an elegant solution that doesn't need any extra moving parts. Just really, really smart design. All right, following that flow, we arrive at our next major landmark, the urinary bladder. And you can forget about thinking of this as just a simple storage bag. This thing is a sophisticated, muscular, and incredibly expandable tank. I mean, this organ is a marvel. It can expand to comfortably hold around 700 to 800 milliliters of fluid. That's a lot. And if you look here, you can see the key players. You've got the powerful detrusor muscle that makes up the wall and the smooth triangular area at the bottom called the trigone. The two ureters plug in at the top corners, and the exit, the urethra, is right at the bottom point. And if we zoom in on the bladder wall, we see a similar 3-layer setup, but it's kind of supercharged. The inner mucosa has these special cells and folds called rugae that are like an accordion, allowing it to stretch out like crazy. And that middle layer, that's the detrusor muscle. It's a powerhouse with 3 distinct layers of muscle, all with one job, to squeeze and empty the bladder. Okay, so controlling the exit are 2 really important gatekeepers. First, there's the internal sphincter. It's made of smooth muscle, so it's totally involuntary. It just relaxes on its own when the bladder gets full. But then there's the external sphincter. This one is made of skeletal muscle, and that's the one you control. It gives you the final say on when it's time to go. So we have a full bladder, we have our 2 gatekeepers. How does the body coordinate the release? This brings us to the grand finale of the process, the neurological command known as the micturition reflex. It's a feeling every single one of us knows, right? But what's actually happening behind the scenes, neurologically speaking? How does that feeling of, okay, bladder's full, turn into the actual command to urinate? It's this beautiful, coordinated dance. It all starts when the bladder fills up to a certain point. Stretch receptors in the bladder wall fire off a signal to your spinal cord. This triggers an automatic reflex. It tells that big detrusor muscle to start contracting and the internal, involuntary sphincter to relax. But, and this is the critical part, that signal also shoots up to your brain, letting you know what's happening. It's your conscious brain, the cerebral cortex, that gives the final green light to relax the external sphincter. This whole system is incredibly elegant and efficient, but its design also has some vulnerabilities. So, for our final section, let's talk about what happens when this finely tuned system comes under attack. A UTI is exactly what it sounds like, an infection somewhere in the urinary system, and the vast majority of the time, the culprit is a bacterium you've probably heard of, E. coli. It's totally normal and harmless in our gut, but if it finds its way into the urinary tract, well, that's when you have a problem. It's a classic case of a good guy in the wrong neighborhood. Now, you've probably heard this before, that UTIs are way more common in women than in men, and this is not a coincidence. It comes down to a really simple difference in anatomy. So what is it? And there's your answer, 4 centimeters. That's the average length of the female urethra. Compare that to the male urethra, which is around 20 centimeters long. It's just a much shorter journey for bacteria to travel from the outside world into the bladder in women, and that anatomical fact makes all the difference. Now, this is really important to understand. Not all UTIs are created equal. A lower UTI, which we call cystitis, is an infection that's just in the bladder. The symptoms are awful, pain, burning, urgency, but they're localized.
But if that infection manages to travel up the ureters and get into the kidneys, it becomes an upper UTI, or pyelonephritis. This is much more serious, and it can make you feel sick all over, with things like high fever and severe back pain.
So, just to recap the key warning signs, the classic symptoms of a bladder infection are that pain or burning when you go, feeling like you have to go all the time, and that sense of urgency. But if you add a high fever and that intense pain in your flank or back into the mix, that is a huge red flag. It might mean the infection has reached the kidneys, and that means you need to get medical help right away. So, as we've seen, this whole system is really a masterpiece. You've got the active pushing of the ureters, the incredible stretch of the bladder, and that amazing dual control release signal. It's this perfect blend of automatic reflexes and conscious control. But that very same design, as we just saw, also has its weak spots, like that short pathway that can make infections a real problem. And that really brings us to our final thought for today. Now that we understand the pretty straightforward anatomy and where the bacteria usually come from, it makes you think, doesn't it? What are the simple, everyday things we can do to work with this elegant design and help protect it?
All right, let's dive right in and talk about the kidneys. You know, we often think of them as just filters, right? But they are so much more than that. They're basically the master regulators for our entire body. So the big question is, what happens when they fail?
I want you to think about this for a second. What if your body was hiding a catastrophic failure and you had absolutely no idea until it was almost too late? Sounds like something out of a movie, right? Well, that's the scary reality of kidney disease. So when we say kidney failure, what are we really talking about? Well, it basically means the kidneys have lost their two incredible superpowers. First, clearing out all that toxic waste. And second, keeping all our body's fluids perfectly balanced. But here's the thing. There are two totally different paths to this failure. Think of it like a tale of two failures. In one corner, you've got acute kidney injury. We'll call it AKI. This is the sudden crash. It happens fast, it's dramatic, but there's a good chance of bouncing back. In the other corner, we have chronic kidney disease, or CKD. This one is the silent killer. It's a slow, progressive, and permanent decline. And trust me, understanding the difference between these two is absolutely crucial. Okay, let's tackle the first one, the sudden crash, acute kidney injury. You can think of this as the emergency room drama of kidney failure. It's fast, it's intense, and it demands attention, like right now. So officially, AKI is this really abrupt, super rapid drop in kidney function. We're talking hours or days, not months or years. And that quick decline causes all sorts of nasty waste products to build up in your blood. But here's the key point, the ray of hope with AKI. It's potentially reversible. If you can figure out what's going on and treat it fast, the kidneys can often recover.
The easiest way to get your head around the causes of AKI is to think of it like a plumbing system, with the kidney being the main filter unit. You can have a problem pre-renal, which means before the kidney. Think of it like not enough water pressure getting to the filter. Then you can have a problem intrarenal, meaning the damage is right inside the filter itself. And finally, you've got postrenal, which is a blockage after the filter, like a clog in the drain pipe.
Okay, quick pop quiz for you, using that plumbing analogy. Let's say someone has a severe hemorrhage, they're losing a lot of blood, or their heart is failing and can't pump effectively. Where does that problem fit? Is it before, inside, or after the kidney?
If you said pre-renal, you nailed it. That's a textbook cause. Both of those conditions mean there's a sudden, massive drop in blood flow to the kidneys. The water pressure is just gone. And just to round it out, an intrarenal problem, damage to the filter itself, could be from certain toxins or drugs. And a postrenal problem, that could be something as simple as a kidney stone or an enlarged prostate blocking the flow of urine out.
All right, so when someone has an AKI, it usually follows a pretty predictable four-act play. First is the onset. That's the moment of the injury itself. Then things get rough with the oliguric phase. Oliguric just means low urine output. So urine pretty much stops, and all that waste starts building up. After that, if things are getting better, you hit the diuretic phase. This is kind of weird. The kidneys start making tons of urine, but they're not great at filtering yet. It's like the factory's back online, but quality control is still shot. And finally, you get the recovery phase, where function slowly, hopefully, gets back to normal. Okay, so we've seen the sudden crash of AKI. Now let's switch gears completely and talk about its opposite, the slow, silent creep of chronic kidney disease. This isn't that ER drama we just talked about. No, this is more like a slow burn thriller with a truly devastating twist at the end. So what is CKD? Well, it's defined as a permanent and progressive decline in what's called the glomerular filtration rate, or GFR for short. That's really just a fancy way of measuring how well your kidneys are filtering your blood. And the key words here are permanent and progressive. Unlike AKI, this doesn't get better. It's a one-way street, usually driven by years of damage from things like diabetes or high blood pressure. And this is what makes CKD so incredibly dangerous, so sneaky. Your kidneys are made up of millions of tiny little filtering units called nephrons. Think of them like workers on an assembly line. As CKD progresses, these workers start to, well, drop off. But the remaining workers, they just work harder. They pick up the slack, they do double shifts, they compensate so well that they create this silent zone where you're losing massive function, but you feel completely fine.
And because of this incredible ability to compensate, get this, a person can lose up to 80% of their kidney function before any major symptoms show up. Just let that number sink in for a moment. Your body is hiding a full-blown catastrophe until the system is on the very brink of collapse.
It's just mind-boggling, isn't it? So why? Why are the symptoms masked for so incredibly long?
It comes down to this incredible biological trick. The remaining nephrons are little factory workers. They undergo something called structural hypertrophy. That means they literally get bigger and stronger to pick up the slack. They are so good at their jobs, they manage to hide the fact that the factory is mostly empty and about to shut down for good.
So whether you get there by the fast train with AKI or the slow, scenic route with CKD, the final destination is often the same. And it's a place you do not want to be. It's a total system meltdown called uremia.
Uremia. The word literally means urine in the blood. And yeah, it is every bit as awful as it sounds. This isn't just a kidney problem anymore. This is a full-body, catastrophic crisis. It's like an avalanche of failures that hits pretty much every single system in your body.
First, let's talk about the filtration failure. The most basic job is gone. The body can't get rid of salt and water, so you get massive fluid overload and swelling, called edema. Potassium levels skyrocket, that's hyperkalemia, which can trigger lethal heart arrhythmias. And the body's pH balance goes haywire, leading to a state of profound metabolic acidosis. It's a chemical disaster.
At the same time, all that toxic waste that should have been filtered out is now just circulating. It poisons the nervous system, which can cause everything from confusion and fatigue to comas and seizures. It attacks the peripheral nerves, leading to damage in your hands and feet, and it wreaks havoc on your gut, causing constant nausea, vomiting, and a complete loss of appetite.
And then there's the part we always forget about. The kidneys are also amazing hormone factories. When they fail, that factory shuts down. They stop making a hormone called EPO, and without it, your body can't make red blood cells. The result? Severe anemia. They also stop activating vitamin D, which is absolutely essential for bone health. Without it, you get a devastating bone disease called renal osteodystrophy. So, we've walked through this complete system meltdown. What's the one big idea you should walk away with?
It really all boils down to this single, powerful point. The kidneys are so much more than a simple pair of filters. Their failure isn't just a clog in the pipes. It is a total, catastrophic collapse of the body's entire internal balancing act, the very system that keeps us alive from second to second.
So, let me ask you, now that you've seen the sudden, violent crash of AKI, the slow, silent creep of CKD, and that full-body crisis of uremia, how does it change the way you think about the kidneys and their incredible role in keeping us healthy?
Today we're tackling a really important topic. What happens when your kidneys start to fail? We're going to break down some of the key terms you hear and really dig into a problem that starts silently, can turn into, well, a full-blown crisis for the entire body. So let's jump right in. So think about that for a second. What if your body was in a state of crisis and you had no idea? That's the truly terrifying part about kidney disease. It's sneaky. It's this breakdown that's happening completely in the background. Your body's amazing filtration system is failing, but for a long, long time, there are zero alarms. No pain, no obvious signals telling you something is seriously wrong. So why so quiet? Well, it's because our kidneys are incredible overachievers. The healthy parts, the nephrons that are still working, they go into overdrive. They actually get bigger and work harder to pick up all the slack. It's this process called hypertrophy, and they are so good at it that they mask the problem until it's almost too late. By the time you start feeling tired or seeing swelling, you could have already lost a massive amount of kidney function. And that's exactly why we have to learn to read those early, subtle biochemical signals, the stuff that shows up in lab work. Okay, so to really get a handle on those signals, we need to learn to speak the language, right? The language of renal failure. And look, these aren't just fancy medical words. They are specific clues that tell a doctor exactly what's going on inside. All right, this is probably one of the most important distinctions we're going to talk about today. You've got to understand the difference between azotemia and uremia. Think of it like this. Azotemia is the smoke. It's the lab result, right? It's the numbers on a blood test that show, hey, waste products like urea are building up in here. It's a warning sign, but you might not feel a thing. Uremia? Well, uremia is the fire. That's when the waste has built up so much that it's actually making you sick. It's a full-blown clinical crisis with symptoms like fatigue, confusion, nausea, the whole shebang. So you can have the smoke without the fire, but you can't have the fire without the smoke. Okay, so let's talk about one of the first big physical clues, oliguria. It just means a really sharp drop in how much you're peeing. I mean, a healthy person makes over a liter a day, easy. But dropping down to this level, somewhere between 50 and 250 milliliters, that's a huge red flag. It's a sign the kidneys just aren't filtering fluid out of your blood, and that fluid is starting to back up. And then you have anuria, which is even more serious. We're talking less than 50 milliliters a day. To put that in perspective, that's less than a quarter of a cup of coffee over an entire 24-hour period. It basically means the filters in your kidneys have almost completely shut down. The whole system is teetering on the edge of total failure. Now, hematuria is a little different. The other terms are about volume and waste buildup. Hematuria is about actual physical damage. It means there are red blood cells in the urine. So something, somewhere along the line is bleeding. It could be anything from an infection to a nasty kidney stone scraping its way through or something more serious. It's a literal sign of injury. So we've got the lingo down. Now let's look at what happens when all these signals add up to that full-blown crisis we mentioned, uremia. This is what happens when that fire really starts to spread. And this image just perfectly shows that domino effect. Look, it starts in the kidneys, but man, it does not stay there. First, the filters fail, so fluid builds up everywhere, that's edema, and potassium levels can skyrocket, which is incredibly dangerous for your heart. Then, all that toxic waste that's not getting filtered out, it literally starts to poison your brain and nerves, causing confusion, what's called uremic encephalopathy. And finally, the kidneys stop doing their hormone job. They stop making the signal for red blood cells, so you get severe anemia, and they stop activating vitamin D, and we're about to see just how catastrophic that is for your bones. So let's switch gears a bit and talk about the physical evidence. What can a doctor actually see and feel during an exam? These are the ways that internal crisis starts showing up on the outside. We're going to zero in on three main things here. What happens to the skin, that classic swelling or edema, and the damage that happens deep down in the bones and muscles. This is just wild. It's called uremic frost, and it's exactly what it sounds like. The level of urea, that waste product, gets so high in the body that it starts coming out in your sweat. And when the sweat evaporates, it leaves behind this fine, white, crystalline powder of urea right on the skin. I mean, can you imagine? It is such a stark, visible sign of just how toxic things have gotten on the inside. And then there's the itching. We're not talking about a little patch of dry skin here. People with uremia often experience this relentless, absolutely maddening itch called pruritus. And here's why. The failing kidneys can't get rid of phosphate, so phosphate levels in the blood go way up, and these tiny little phosphate crystals start forming and depositing in the skin. It causes an itch so deep and persistent that nothing seems to relieve it. So we talked about edema, the swelling. It's pretty straightforward. If the kidneys can't get rid of salt and water, where does it go? It backs up into your body's tissues. You see it a lot in the legs and feet, because of gravity. And it often leads to something called pitting edema. This is where if you press your finger firmly into the swollen skin, it leaves a little dent, a pit, that takes a while to bounce back. It's a classic sign of that excess fluid. And this is a really critical point to grasp. We think of kidneys as just filters, but they're also major players in our endocrine system, our hormone system. They perform a hormonal job that is absolutely essential for healthy bones. And when that function fails, your entire skeleton is at risk. So let's walk through this devastating chain reaction. First, your kidneys are supposed to take vitamin D and turn it into its active form, called calcitriol. When they fail, that process just stops. Now, without that active vitamin D, your intestines can't absorb calcium from the food you eat. But here's the kicker. Your body has to, it must, keep blood calcium levels stable for your nerves and muscles to work. So what does it do? It panics. It releases hormones that basically raid your bones, pulling calcium out of them to keep the blood levels normal. And the result of this constant raiding is a painful condition called renal osteodystrophy. Your bones become weak, brittle, and prone to fractures. Okay, so we've gone from lab results all the way to decaying bones. Let's pull it all together. Why does understanding all this, especially the difference between these key terms, actually matter? It really all comes down to one thing: timing. It's about catching the problem early. Recognizing azotemia. Remember, that's the silent smoke on the lab report. That's everything. That is the window of opportunity for a doctor to step in, to slow things down, and hopefully to stop the patient from ever getting to that raging, multi-system fire of uremia, where the damage can be catastrophic and even irreversible. And that really leaves us with a final, bigger question, doesn't it? Our bodies are constantly sending out these little biochemical messages, long before we ever feel sick. So it makes you wonder, what other silent signals are our bodies sending out right now that we just haven't learned how to decode yet?